Hello physics, welcome to another flipped lecture. The background has changed. We are no longer in my classroom. I am off. It is summer break, but I'm still working for you. So I hope you enjoy the change in background. Welcome to my front porch swing. I hope that you enjoy it as much as I do. Sorry it's a little backlit. That's okay. You see my face all the time. You don't need to see my face. We're looking today at Chapter 13. Now Chapter 13 is almost entirely review. There is very little new information here. Okay? And so we're not even going to talk about 13A. It's stuff that you knew very well from chemistry. So don't worry about 13A. Just look at 13B, and that's what we're going to be covering here today in the lecture. And even a lot of 13B is review too. So we're going to be kind of zooming in on the new concepts for you here in physics that we didn't cover in chemistry. The first one is stress. And I'm going to have to be moving my little webcam around a couple times here today because there's no good place for it. Stress is measured in the unit called a Pascal, which is the same unit, if you remember from chemistry, that we use to measure air pressure or water pressure. And the concept is the same. It's newtons per square meter. So like surface pressure or gas pressure in a bottle is how much the gas is pushing on the wall per unit area of the wall. Here we have how much force is going on in an object as it's being stretched per unit area within that object. So we use the symbol sigma. Sigma is the symbol here. That's the lowercase parallel to the letter S in Greek. Okay, and a tensile force pulling on an object creates stress on that object. We measure that in newtons of force per square meter of area, and we're looking at the cross section there. So we don't care about how tall it is. The volume of the object doesn't matter. It's just the perpendicular cross-section to the direction of the force, and you'll see plenty of examples of that later on. Okay, the formula for that is sigma equals force over area, so force divided by area in square meters. A similar concept is the concept of strain. So in strain, we don't look just at the cross-section. Now we care about the length of the object. Because now we're looking at, okay, after it has gone through a certain amount of stress, did its shape change? Did its size change? And again, we're looking at the dimension of the object that is parallel to the direction of the force. So you're pulling on an object and then you measure it afterwards. And did it get any bigger? Okay, so we use the lowercase letter epsilon here. This is, again, the Greek parallel to the letter E. It kind of looks like a letter E. This is epsilon, though, not E. Epsilon equals the change in length divided by the length. So what was it before? What is it now? Subtract, get the difference, divide that by the original length, and that'll give you a percentage change. All the units cancel out in this. You have meters in the top, you have meters in the bottom. Meters divided by meters is nothing. So there's no units to strain. Epsilon equals some decimal answer. Okay, let's look at some examples here. So here we have a tension machine, a tension force machine, putting a particular amount of tension on this little metal strip. So again, move myself. So actually, I'm going to go over here because there you go. That's better. This metal strip is 2.5 centimeters wide and 0.3 centimeters thick, and it's under 500 newtons of tensile force. So what is the stress? Now, 500 newtons, that's my force. The area I have to calculate. But before I can calculate the area, I need to make sure that I'm measuring in meters. And I wasn't. I was given numbers in centimeters. So let's convert. Centimeters here, 2.5 centimeters is 0.0250 meters. And 0.3 centimeters is 0.003 meters. Okay? So now sigma equals force over area. Force is 500 newtons. The area is just 0.0030 times 0.0250. Quick multiplication. I know 3 times 2.5 is 7.5, and there's 2 zeros in front over here, and another 0, and there's lots of zeros. But if you plug it in, it's pretty simple. Here we have 0.0000750 square meters. That's my cross-sectional area. 500 newtons divided by that gives me basically a gigantic 2/3 number. There are 7 sixes and then a decimal point and then an infinite progression of sixes until you decide to round to 7. Pascals. I only have 2 significant digits up here in this number, so I can only express 2 significant digits. So 6,700 pascals, sorry, 6,700,000 pascals, and then to express that in scientific notation would just be 6.7 times 10 to the 6th pascals. Okay, so that is a calculation of stress. Now, calculation of strain under that same load. The metal strip, which was originally 10 centimeters long, is found to be 10.2 centimeters long. What was the strain? So all the units cancel. You don't have to worry about converting between centimeters and meters. Just if you're given units that aren't similar, you got to make sure that they're all the same. But once they're all the same, it doesn't matter what it is. It doesn't have to be all in meters. Okay. So we have here a piece of metal that has been stretched, and the stress on it produced a strain. So sigma equals the change in length divided by length. 10.2 minus 10 is just going to be 0.2. Divided by 10 is 0.02. So epsilon equals 0.020. That is the strain on this piece of metal. And again, remember, it's the cross-sectional area, not the length. We don't care about the volume. I'm sorry. It's the cross-section for stress. It's the length for strain. There you go. Let me say that properly. Okay. One more concept here, and that is Young's elastic modulus. And so you get to calculate how elastic something is. Young's elastic modulus is calculated with the, or uses the capital letter E as its symbol. It measures how much an object changes per unit force, per cross-sectional area. So it grew by a certain amount because of this stress that was put on it. Okay, and this talks about a substance's hardness or its brittleness or its malleability. So in a quick example, steel is much harder than rubber. If you put the same stress on a piece of steel, it's going to very, very slightly change, maybe not change at all. You put that stress on a piece of rubber and it's going to expand. So elasticity is how much does something move with a certain force. And a related concept is the concept of work hardening. So in this idea, the more you beat something up, the harder it gets. So a great example would be steel. A blacksmith will take a piece of steel, put it in the forge, get it red hot, take it out, hammer it, and then quench it, put it in the water so it cools off, and then put it back in the furnace so it heats up again. It gets red hot, they take it out, they hammer it some more. They keep doing that. Why do they keep dousing it in the water? Why don't they just go fire, hammer, fire, hammer? Well, it's the cycle of stress caused by heating and cooling that actually makes the steel stronger. So it's called tempering when it's steel, but the same things happen for other materials as well. Generally, the term is work hardening. Okay, so let's look at some pictures here. Here we have a picture of that same piece of metal, and we have subjected it to a certain stress, and it has responded with a certain strain. And so I want to know, how elastic is that piece of metal? Well, the elastic modulus is sigma divided by epsilon, stress divided by strain. Here's my stress, here's my strain. I do the division, I get 3.4 e to the 8th pascals. It's a very large number. Generally speaking, the larger the number, the harder and more brittle something is, the less it's going to change because of stress. So rubber would have a very low number here. Steel is a very high number there. Okay. So another idea here, we've been talking about tensile strength and stress and strain, and can you represent this graphically? Yes, you can. Stress and strain can be plotted on a graph, and then this essentially gives you the Young's elastic modulus at all different measurements, and shows you the line that is created when you graph Young's elastic modulus at various sample points. Okay. And so there are some terms there. We're going to see something called a proportional limit, and that's the point where some deformation begins to occur, where the object doesn't just return to its original size when you take the stress off of it. The elastic limit is the point where permanent deformation happens, and it's usually just before the object fails with the amount of stress that you've put on it. It's going to start stretching really easy. And then the fracture point is where the object breaks. So let me show you some pictures of these graphs. Okay, so here we have a brittle material, a very hard material that doesn't change very much in the strain category for all the stress that you put on it. So increasing stress, it does change a little bit, but it doesn't change very much. And very, very hard things tend to, when they fail, they don't ever get to an elastic stage or a plastic stage. They don't stretch, they just break. So this is the case with hardened carbon steel that they use to make like pocket knives and swords and things out of, where it needs to be very hard. You don't want it to bend, but if you do put enough force on it that the metal fails, it just shatters. Okay, it's never going to stretch. A strong material that is not ductile, like steel wires, okay, they will stretch a little bit more with the stress, and then they will get to a point that we would call the proportionality limit, and then it'll bend, it'll warp for a minute, and then it'll break. Okay, so they break with just a little bit of warping just before they do. And then ductile materials have this area where you apply more stress, and then it gets to a point where it's not going to just spring back to that size when you take the stress off of it. It's going to start to deform. And then it gets to a place called necking, and this is a weird name, but it's where the graph looks like a hump here, and you can put stress on it, and then if you take the stress off, it still stretches. It still has strain going on. It's permanently deformed, and it usually breaks right after this necking shape. Okay, and then if you have a smooth plastic material like rubber or you know, some kind of stretchable like silicone material, you put just a little bit of stress into it and you get huge strain, huge change in deformation and shape. Okay, so this is a relationship between stress and strain in Young's elastic modulus. Here's another example. You have a section where the graph is linear and elastic. If you let go with the strain, it'll bounce back down to this size. You go beyond that point, it's still elastic, but it's no longer a straight line. And at this point, it's going to deform permanently some amount. You keep pulling, and there comes a point where the object is just stretching, and it's about to fail. Little bits of stress will bring it up to large amounts of strain. You can even lack off on the stress, and it'll still stretch, right? And then you get to a point where it fractures. So these are all of the points that you will tend to see in your graphs for your homework or your classwork. We've been talking this entire time about tensile pulling force, and the book leads out with that force, but there are some other forces as well. There's a crushing force, sometimes called a compression force. It's the same idea, where instead of pulling on an object, you squish the object and you move the molecules closer together. That's a crushing force or a compressing force. Shearing force is when you take the object and you rip it in two different directions, okay? Force which causes motion along parallel planes in the material, but in opposite directions. So the reason that shears or scissors are called shears is because they shear objects. It puts one blade on one part of the object, the other blade on the other part of the object, and it goes like this. And so the object breaks because of shearing force. So they're called shears. Both of these kinds of forces can also cause stress and strain, and you measure them the same way. So don't get stressed out about that, and don't strain over how you calculate them. Huh! Oh my goodness, I'm so clever. Okay, just pictures for the different kinds of forces again. So a tensile force pulls, a compression force or crushing force pushes together, a shearing force goes in opposite directions. Okay, when something fails because of tension forces, you see the middle part shatter out, and the two halves come apart. Okay, this just broke, and these things go opposite directions. Compression forces, when you see those things fail, the middle will bulge because of the compression forces. Okay, and then a shear force, when an object fails because of shear forces, you'll see two halves of it move in opposite directions. So those are the three kinds of material forces. Okay. Last little thing, there's one term from the back of the chapter that you haven't seen yet in chemistry, and that's regelation, regelling. So the idea here, it's in the context of phase changes. You already know about melting and freezing and evaporating and subliming and condensing, and all those words are familiar to you. This is a new word that you haven't seen yet, and this is when a solid goes to the liquid phase, not because of a temperature change, but because of a pressure change. You can increase the pressure on a solid to the point that it liquefies, and you didn't get it any hotter, you just increased its pressure. Not all substances will do this. but many of them will. Water is a great example. So I have a picture here for you of a famous experiment where you take a block of ice, and the block of ice is on 2 wood blocks that are also as cold as the block of ice. You put this whole thing in the freezer, and you have 2 large metal weights connected by a thin wire, and the metal weights and the wire are also just as cold as the ice. You put the whole thing in the freezer for a long time. Then when you set the metal wire on top of the ice, the weight of these weights on this metal wire actually melts the ice underneath it. So the wire slips down and the water molecules move up and refreeze. And so when you're done, you still have a solid block of ice, but this wire has passed through it, melting and refreezing as it goes, and that is called regelling or regelation. It's a fun word. There you go. That is the end of it. If you have any questions, please post them in the comments field below, and I will see you tomorrow in class. God bless you. Have a wonderful day.